Welcome to this explainer. You know those massive oil-immersed power transformers that keep our cities running and the lights on? Well, when things go wrong inside them, it happens insanely fast. Today, we're diving into the high-stakes world of electrical grid protection to look at the ultra-fast mechanical hero keeping these massive machines safe from total catastrophic failure.
To really get a sense of the stakes here, I want you to imagine 10,000 degrees Celsius. That's what we're dealing with. If an internal electrical arc fault happens, it literally vaporizes the transformer's insulating oil instantly, at temperatures exceeding that 10,000 degree mark. It essentially creates a literal ticking time bomb right inside the steel tank.
So here's our agenda for today. First, we'll look at the transformer time bomb, then dive into the anatomy of the PRV, walk through the millisecond trip sequence, weigh the key advantages and limitations, and finally do a little showdown, PRV versus the Buchholz relay.
Let's jump into part one, the transformer time bomb, or the catastrophic threat of internal arc faults.
You see, an arc fault creates a rapid pressure wave that can reach truly dangerous levels in a matter of milliseconds. Without a way to instantly relieve it, that massive temperature spike we just talked about creates a pressure buildup so intense it'll rupture the thick steel tank, spill burning oil everywhere, and set off a massive, uncontrollable explosion.
Which brings us to part two, anatomy of the PRV, our purely mechanical last line of defense.
Enter the transformer pressure relief valve, or PRV relay, our simple, incredibly fast hero. When you actually look at this device out in the field, it's remarkably unassuming. It's just a weather-resistant stainless steel or aluminum enclosure mounted right on top of the transformer tank. It's a purely mechanical unit sitting right there on the wall, completely independent of any complex electrical sensors. And inside that housing, it relies on just 4 essential mechanical components working in perfect harmony. The star of the show is the pressure-sensing piston. Think of it as a mechanical transducer. It converts that dangerous fluid oil pressure into physical movement upward, pushing against a precisely calibrated steel spring.
Moving on to part three, the millisecond trip sequence, where we see things reacting faster than the blink of an eye. During a real high-pressure fault scenario, that internal arcing pressure shoots up almost vertically. We're talking about hitting 200 kilopascals in just 20 to 50 milliseconds. It completely proves why traditional electrical numerical relays, which actually need time to process signals and run calculations, are just way too slow to stop the explosion. Because it's so fast, the PRV has to progress through 6 precise stages in an absolute flash. It starts in a dormant detection state, jumps into action during that rapid pressure rise, and decisively pushes past the spring's physical threshold. Once it crosses that line, boom, the piston slams the electrical contacts shut. That critical contact closure happens instantaneously, usually in just 20 to 100 milliseconds. Now, once those mechanical contacts close in stage 4, the relay completes a circuit that essentially commands the main circuit breaker to activate. Modern circuit breakers receive that signal and fully open within 50 to 100 milliseconds. That completely isolates the faulted transformer from the power source right before structural failure becomes inevitable. Let's jump into part 4, key advantages and limitations, balancing raw speed with diagnostic reality.
Like any great piece of engineering, the PRV's biggest strengths come with a few trade-offs. The absolute standout advantages are, of course, that unmatched ultra-fast response of 20 to 100 milliseconds, and its completely independent mechanical operation. It's got over 100 years of proven reliability. Plus, it's perfectly immune to false trips from harmless startup currents, those transient inrush currents that easily confuse highly sensitive electrical relays.
But on the flip side, it's a pretty blunt instrument. Its main limitation is that it provides very limited diagnostic information, essentially just a binary trip signal. It yells, yes, pressure spiked, but doesn't identify the specific fault type. Also, because it's physical, it's vulnerable to dirt or moisture in the oil. And that spring, it can suffer from material fatigue or spring drift over its 10 to 20-year lifespan, which means it requires regular testing to make sure it's still perfectly calibrated. All right, bringing us to part 5, PRV versus the Buchholz relay, the ultimate showdown in transformer protection. To really appreciate the PRV, we need to compare it to its famous counterpart in power systems, the Buchholz relay.
On one hand, we've got ultra-fast mechanical pressure detection with the PRV. On the other, moderate-speed gas accumulation detection with the book holes. They're both heavily relied upon to protect the transformer, but they operate on entirely different physical principles to catch entirely different types of failures.
Basically, the PRV is your rapid responder. It's there for those sudden, violent internal arc faults that cause immediate pressure spikes. The book holes, however, detect slow, incipient faults, like slow insulation degradation or core faults, by measuring dissolved gas production. But here's the kicker. Because those gas bubbles take time to collect and trigger a mechanical pendulum through buoyancy, the book holes can take up to 2 full seconds to trip. That's 500 to 2,000 milliseconds, compared to the PRV's 20 to 100. Which leaves us with a really fascinating thought to wrap up today's explainer. As our modern electrical grid gets infinitely more complex, relying on highly sophisticated digital sensors and numerical processing, we are still relying on century-old, purely mechanical ingenuity as our last line of defense against explosive disaster. It really makes you wonder, doesn't it? What other incredibly simple mechanical devices are just quietly hiding in plain sight, saving us from disaster every single day?